said, Gary Pomerantz from Flack and Kurtz. Welcome, everyone. Just a couple things before we get into the slides. Just a brief overview for the project. Give you an idea what's in it. Up on the roof, we would have, as we typically do, cooling towers to reject the heat from the building, and we have emergency generators for life safety rules over system. Hearst has the heat running when the lights go out. On this building, we elected to go with large built-up AC units to serve the building as central units instead of locating systems on each floor. And as it says on the slide, what it does is when the temperature outdoors is less than, say, the space indoors, you get a tremendous amount of free cooling. And when the temperature is below 55 degrees, which is most of the year in New York, you cool the building for free, which is a good thing. It's a very energy efficient thing. And energy efficiency is one of, we'll say, the 5 key parts of the LEED certification system. You use low temperature air. One of the challenges is, while you put all the equipment in one place, it's good. If you use normal temperature air, say 55 degrees, you bring it down the building. It uses very large spaces. It's very inefficient as far as the architecture goes and as far as the use of the building. We went with overhead air. And as we work our way down to the basement, that's where we have some more large air handling equipment to serve, say, the central atrium space, and the chiller plant, and the stormwater collection system, the big tanks. Just to go over this, on this project, there's a lighting control system with all the glass on the building. It's not only to let you look out at the city and give the occupants great view, but it also emits a tremendous amount of light to the building. So once you do that, you start to measure how much light's coming in, and you decide, do I leave the lights on? Can I dim them? Can I turn them off? And again, it's a tremendous energy-saving measure for the building, because in New York City in the summertime, if you can save on lights, you can save 15 to 20 cents a kilowatt hour, and that's a lot of money. The air handlers are at that zone of the building, as we discussed pretty much before. This was done on LEED 2.1. It's recently been updated to 2.2, which in these buildings we have very high efficiency filters, which is required, and it's good to clean up the New York City air, which isn't always the best to breathe. We also humidified the building. That's been eliminated from the current LEED guidelines. The key is to really, not only to make a building that is more energy efficient by LEED, it's to really improve the overall experience and overall quality of the time that you spend in the building. So they look for things that have been discussed tonight, which is using less resources, such as reusing the existing building, making use of a lot of recycled content in the materials, indoor air quality, to improve the indoor air quality of the building. We also humidify the space, and which is nice. In the winter, you don't get stacks, you don't get static shocks, you don't get dust and various other things, and it's better for your respiratory system. It did impose challenges down in the lobby. As we saw, or Alex was describing, there is an uninsulated wall to the existing building. When you have a humidified building and uninsulated walls, you have to actually keep them warm, otherwise condensation becomes evident, and that's not good. Low temperature air we discussed. It's really a very efficient way to move air. It lowered our fan horsepowers and really took a lot less space out of the building. And the heat recovery from the tower, when we get to the atrium discussion in a minute or two, that's still clean air that we were exhausting from the building. It's a general spill that you take 20% of the air in New York. As you make it up, you tend to just blow it out of the building. And what we did is, it's already been heated or cooled, depending on the season. It's had its humidity control. We get a second run out of it, a second life. We bring it down through the lobby. It's used again, and at that point, it's either drawn out through the kitchen exhaust system, which is down in that zone, or it's spilled out of the lobby. So we're getting, I guess, an extra bang for the buck, so to speak, on that. Give an idea for the energy consumption. You heard before this 22% number, but you can see across the board, lighting's reduced. A lot of that's from the lighting control and the layout of the lights. Heating is a little higher, but that's what happens when you have floor-to-ceiling glass. But again, we're looking at the overall bottom line. Cooling numbers are about the same. Fan energy is way down with low temperature air. Pumps are way down. It's incredibly reduced. And for the bulk of it, miscellaneous power is something. It's the requirements really of it. I mean, you have say it's a data-intensive environment, and that's what's raising miscellaneous tower, but overall, the bottom line is 22%. It's not bad anymore. It's a tremendous cost savings. Once you reduce your electrical use, you reduce your nitrogen oxides, eliminate your brown skies, pretty sunsets, eliminate your sulfur dioxide, which makes your acid rain, eliminate your CO2s. You can see the actual numbers. It's a tremendous amount of emissions that were reduced from this building. Water conservation. We talked about before how we collected the rain rain off the roofs, and we collected the storage tanks down in the basement. I think we went with a 1 in 10 year storm. We didn't go with a 1 in 100 year storm. It was right size, so to speak. And that water, while it's not good for potable use for drinking, it's great for cooling tower makeup if you do the right water treatment, but it's free. Water is a very valuable commodity these days. We've used low flow fixtures throughout the building. The faucets, you can't leave them on. You put your hands in, they start up, you move away. And while it seems commonplace, they're not done on every job. So you can see fixtures alone reduced our water consumption by over 1 million gallons a year. Irrigation, use the rainwater. And why use hose from the tap? The plants would naturally get watered by the rain. We use it for irrigation. The cooling tower, believe it or not, the cooling tower is probably the largest consumer of water in a building. All the energy in the building goes to boiling the water out of a cooling tower. So you can see it's only 4%. This cooling tower is such a tremendous use. And in New York City, to reduce the stormwater runoff is a great thing because New York City, especially Manhattan, uses combined sewers. So that means we take the sanitary and the storm through the same pipes in the street, and it goes through the same treatment plant. And during bad rainstorms, the treatment plant can't handle it, and as bad as it sounds, they have no choice but to discharge that mixture of rain and sewage into the waterways. So to be able to use that water and take the load off the sewage plant is good for the Hudson River, good for us. So you can see the overall water savings in a year by collecting rainwater is, well, the rainwater, the low capacity fixtures, it's up to 1.7 million range. You can see in the lobby is the large water feature that was discussed. And the intent is to really use all the makeup water from there, which will be very little, we'll go over that in a minute, from the rain. Why use city water? There's an abundance of rainwater that's collected. You can see the lobbies, we saw this before, but it's a very large, very tall volume space. Really the people walk on the lower levels, and there's no one up here. So as we went through this, we said, why air condition all the way up high when the people are down low? So what we did in the lobby is we put a couple features in. Like you said, is we spilled the air down from the tower. That would only be thrown out onto the street, so to speak. We used a radiant floor. I'm not sure if everyone's familiar with it, but what we did is we installed polyethylene tubing in the floor, which we run water through. And depending on whether we're trying to heat or cool, you either keep that floor temperature warmer than air or cooler than air. And water is a far more efficient way to transfer heat than air. It's more dense, you move less of it to do what you're trying to do. So on a bright sunny day, when the sun comes in through, we'll say, the skylights that we saw on top, or it's coming in through the walls, and it's just warm, we keep the floor cool. So here you're down occupying the lower 6 feet of the space, and that's really where you're trying to adjust the temperature. In the wintertime, you walk in from the outdoors, cold air blows in through the airlocks, and it comes across the radiant floor, and it's warmed. And again, it's in the zone that's occupied. We have to get in, have to provide ventilation there, because there are people there. So we have to do that through displacement ventilation, which is, instead of the traditional, if you looked in this room, you'd see up on the ceiling all these diffusers providing overhead air. No one's up there. And what we do is you force the air out of there at a very high speed. You mix up all the air in the room, which is got the contaminants that rose up, and you bring it down to the people. And it causes greater energy use, causes a lot of other things, forcing air quality. So what we do is displacement cooling. We blow the conditioned air in essentially at nose level, down low, to keep you in the ventilated zone. Then there's the water feature that we discussed. Water features, they're great. They're very pretty, but if you have a water feature traditionally in the summertime that just recirculates the water, it gets up into the 80s in temperature. So what happens is that that accelerates evaporation from the water. So now the lobbies start to get humid. So that means you have to turn your air conditioning higher to remove the moisture from the air, or very often you walk into lobbies where they didn't take that into account, and it kind of smells like a wet lobby. So what we did here is that water is actually cooled. We keep it just slightly above the dew point. So what it does, it actually provides a convective and radiative cooling effect to the space. But even more important, you don't add moisture to the room. So by not adding moisture to the room, you save on the AC load, which saves on energy. You save on water that we would have to replace here for makeup, and the water that comes out of the cooling tower, because you're evaporating, that energy ends up coming out of the cooling tower. So overall, it's not just a visual feature to the space, as most people would see. It's actually an integral part of the conditioning system. Well, we went ahead and we put all this stuff in. We had to come up with a way to model it. So CFD stands for Computational Fluid Dynamics. It's a mathematical model that we build through a computer program. And what we do is we have cold surfaces on the floors. We try to model the air that blows into the space. We put lighting loads in, we put sun loads in, and while the atrium goes up very high, we're maintaining comfort in this zone here. And you can see it's roughly in those temperatures over here, the 75-degree range, which is considered that's what we want to design to. In the occupied office space, again, sun comes in, so you have a choice. You have blinds for glare control, you have light sensors to censor daylight penetration. From that, we adjust the lights, which are low glare in the first place, to make it easier to look at the screens. And the glass performance that was talked about before is it's really a very high-quality glass. In the last 10 years, glass has reached new levels of performance. And what it does is essentially half the energy from the sun is in the invisible wavelengths. You can't see it. So if you can remove that, that's what these coatings do on the glass, you immediately reduce your solar load by half. But you haven't even put any color in the glass yet. And then on top of it, for visuals and things like that, you can add some color to the glass. So when there was a shading coefficient before quoted of 0.27, I think, that means we've removed 73% of the energy of the sun right there. It never even entered the space. 60% of the light's coming in, so you don't have a dark glass.